Hello everyone, myself Shraddha Agarwal. This is a part 2 video of a DMA-based design using the RFSoC. In this video, I'm going to talk about the SDK code. That is the basically DMA scatter gather code, how we are configuring the DMA, setting up the buffer descriptor for transmitter and receivers. And so first what you need to do, you need to go to the SRC folder. Here you can see all the C files are available here. So I'm going to the main.c file. So initially all the header files are included in this file. Then we are initializing the command structure. So we have a different command that we are using, that is like for the checking of the calibration status, power on status, playing DMA, capturing DMA as we checked in the last video. So here first when FPGA get programmed, we can see on the data term window hello world get print. After that it will display the version ID. Then you can see we are configuring the clock over here. So in this ZCU111 board we have a two clock, that is one is the reference clock and other one is the sampling clock that we are setting by using the reference clock. So LMK4208 is the reference clock that we set it at 122.88 megahertz right now. So first this function is setting this reference clock over here through LMK042008 clock configuration function, and after that I'm setting up the DAC and and ADC clock. So right now we have a frequency of 1.47456 gigahertz. So we are setting it up over here. So now you can see these functions are defined in the xrfdc clock.c file. So as I'm going to the whole file, so you can see over here. So all the functions are defined over here. So this is the first one, that is setting up the reference clock. So here you can see there's a different reference clock that is already defined. So you can select the options what you want to have it from here. So right now we are using 1.2288 megahertz. So you are setting it to the 0. So as you can see in the main.c files, when you are calling the function, you are setting the parameter to 10. And in the same way for LMX2594, you are setting it to the 1.47456. So you can see over here. So all the registers value related to that sampling frequencies are defined here. So that is for the 5.12 gigahertz, 1.47456. So you can set the value by giving the sampling frequency value, by passing the sampling frequency value as a parameter to the function. Then it got automatically taken. It is, yeah. So if you want to change for the other sampling rate, you can change it from here only. You can put that value over here. That function or that sampling frequency register file need to be defined in this C file under this. Now going back to the main file. So you can see after configuring the clock, then design is ready to use. So now you can see there's a lots of options coming on the diagrams window. So now I'm going to the, so basically we are using the two main command, that is a play DAC and then ADC capture. So I will go to the play DMA.c file. In this play DMA.c we have defined the DMA scatter gather code. So in this what we are doing, first step is to configure the DMA, then setting up the MM2S channel and S2MM channel. Then we are creating the buffer descriptor. for the transmitter end, then we are creating the buffer descriptor for the receiver end. Then we are initializing the buffer descriptor, sending the buffer descriptor to the DMA. Then we wait for the DMA to complete the transfer and then free the buffer descriptor. So right now we have a two different file, that is a play DMA.c and other one is the capture DMA.c. So first is for the transmitter, that is a transmitting the data from DDR memory to the DAC, and then for the capturing we are capturing the data from ADC to DDR memory. So in the transmitter function, as you can see over here, so first we are initializing the DMA instance pointer, and then we are assigning some address, a fixed address location for the BDs over here. Then you can see we are initializing the transmitter DMA. So here we are initializing the DMA configuration pointer. So DMA configuration pointer, through the DMA configuration pointer we can copy the all the information related to the DMA hardware in this config pointer, then initialize the DMA instance with the configuration file. So after that, we are going to set up the transmitter channel of the DMA to ready for the packet transmission. So first we are defining the pointer, that is a TX ring pointer, that is a structure containing all the information of DMA instance and descriptor. That is what is the start descriptor, what is the end descriptor, how many um, descriptors are there. So this PD count, as you can see in the parameter, the PD count define how many descriptors you are we have in at the transmitter. Then bytes per BD define how many bytes we are sending through a BD. Now moving forward, this transmitter ring pointer, we are copying all the DMA parameters in the structure, like what is the maximum transfer length, what is the uh, initial buffer address. So all these things we are copying in the transmitting ring pointer. After that, we are creating the BD. So in this BD ring create, we are giving the base address. What is the initially base address of the BD? So here it is giving the physical address and it is the virtual address. So in our case, both are same. So we are giving the same address. Then we are giving the BD minimum line. What is the minimum gap between each BDs? And then we are giving the BD count. That is number of BDs we are going to create. Then we check the status of the BD. In the same way, we create a template and set all BD to same as the BD template. So what we have, so when we create the BD, so first two location indicate the address of the next BD associated with it, and rest of the feelings get initialized to some value or can initialize to zero value also. So by using the BD template, we are initializing all buffer descriptor with the known value. So by using the BD ring clone, we are just cloning this BD in the multiple. So we have a multiple number of BDs over here. So we are cloning the same template in all the BDs. Then we are enabling the cyclic mode, DMA mode over here. So in this cyclic DMA mode, what we are doing, we have a number of BDs over here. So when DMA will reach at the last BD location, then it will come back to the first PD and then start transmitting from here. So in this design, we are using the DMA mode in the cyclic mode. After that, assigning the in this XXI BD ring star, we are assigning the address of the tail descriptor and setting the RS bit to 1 to start the DMA. So same form, same format is defined in the receiver setup also. So this is the transmitter setup. Now sending packet through the DMA. So for sending the packet to the DMA, we need to pass the command that is a xi DMA get transmitter ring. So here we are passing the pointer to the transmitter ring pointer. So what we are doing, we are attaching the buffer uh, to the all the buffer descriptors, so we can start transmitting the data. So DMA will start fetching buffer and reading the data and pass it to the IP, and then output we are going to receive from the IP will be taken by the DMA, receive buffer and written to that particular address. So in this we are setting up the BD using information to packet to transmit. So here we are using the set buffer address. So first we are setting up the buffer address over here. We define the buffer address here, and is a transmitting buffer base that we defined initially as a constant parameter, and then we are passing it to the BD pointer. Then after setting up the buffer address, we set the buffer length at the control register and start of bit and end of bit. So in the BD set length, we are setting up the how many bytes per BD we are going to transfer. At the end, we are going to set start of uh, at the end we are going to set a start of bit and end of bit in the control register. So as we have a multiple number of BD, so we need to set this values. So once it will get set, then our hardware is going to ready to transmit the data. So now when we send this DAC play command, it calculates the first value of the buffer descriptor, how many buffer descriptor we are going to have, and then it start the DMA and then begin the cyclic transform from the transmitter buffer space. So as you can see in this functions, we have a transmitter ring pointer. So here we are assigning it to the get transmitter ring. Then what we are doing, we are doing the PD count calculation over here. So number of bytes is the value we are giving with the tag play command over here. So accordingly it calculates the number of BDs we are going to use. Then bytes per BD depends on the BD count. So we have a number of bytes given, like we are giving the command DAC play 256. It means 256 kilobytes of data we are sending upon number of BDs count that we got from here only. So then we are setting up the transmitter and receiver channel to ready to transmit and receive the data. So we are in the status register file, we are looking for the status and transmitting is uh, get successful or not. So once a transmitter get activated or start, then we started sending the packets, like how many bytes we are going to send per BD. At the end, we send a DAC stop command to just stop the DMA for playing the data to the memory. And in the same way, we have a capture DMA.c file. So in this, we are defining the first, we are defining the receiver buffer, and then we are sending the descriptor to the DMA. Wait for the DMA to so in cap DMA.c file, we are creating the buffer descriptor for the receiver and then sending the descriptor to DMA to receive the data and then free the descriptor. So here you can see we are have a receiver setup, and this also we are in this receiver setup is basically used, we are using for capturing the function to initialize the DMA buffer descriptor and start the receiver DMA. So also we are creating the BDs over here, then we are initializing it to the 0 BD clear, then through the BD template we are cloning or copy the BD template to all the BDs, then we are setting the RS bit to 1. Then by the BD ring allocate functions, we are attaching the buffer. We are defining the receiver buffer address over here, and then we are setting the buffer address followed by the setting the buffer length of the BD. Then we allocate this BD to the hardware, and then RX DMA channel get started and start transferring the data. So this is my whole receiver setup, and then when we call this function, that is a ADC capture, it calculates the number of bytes or how many data we are going to receive it. So first it initializes the DMA, and then it calculates the BD count, how many BDs are required. So when we give this command, that is like ADC capture, then we get the amount of data we are going to capture, then it get calculated, that BD count number get calculated, and then how many bytes per BD we are going to receive. Then we check the status register of the setup, that uh, key transfer is completed or not. If not, then you will get this error message. If it completed, then automatically it gets success. And at the end, you need to see the BD. So basically, DMA start fetching the buffer descriptor, reading the data, pass it to the IP, and then output of the IP will be taken by the DMA and written at that particular given address. Then we read the status register of the DMA channel to know the operation is completed or not. And then if operation is completed, then we will get the status as like successfully. So this is my transmitter and receiver command. So one thing more I just want to tell, key through this DMA we can also send the different waveforms to the transmitter buffer memory speed by specifying the data, how many data we want to transfer. So we have a DAX sawtooth. It is basically generating the sawtooth wave pattern that is transmitting to the transmitter receiver buffer space. So you need to give the number of bytes you want to transmit to the command, that is DAX sawtooth, and then you can give the number of bytes you want to transfer. So in the same way, we can generate the DAX sine and cosine wave also. So we have a function defined over here, and then for the sine also we can fill the memory with the real sine wave by giving this command. So we don't need to go to the MATLAB to generate the input file. We can also generate the input directly from here, and then we can get the output at the receiver end, at the ADC end. So this is all about the DMA scatter code. That's all. Thank you.